You.
Yeah, good.
Hey, Chris.
So I don't know if you guys have an agenda. I have been assembling stuff. I wanted to be more organized, but I just shot you guys an email that has some of my thoughts down in writing in case that
Perfect.
makes it easier
Go for
Yeah,
it.
I
Yeah,
just
yeah.
to talk
received it.
about.
Thanks.
Oh,
Yeah,
okay.
yeah. Go for it.
Yeah. So I have infinitely many questions, but probably I could do some of, like definitions of things as I was going through the quantum free energy paper. But the more interesting and specific questions are something that just hit me last night. So there's like two main topics. One is like, what's the organizing principle for embryos and where is it? And what's that telling us? And the other one is, okay, what's the definition of a thing and how does that get us anywhere in cognition? And the two are sort of beginning to merge in my mind, although, I wish I understood all of your papers better. But the thing that occurred to me last night is about the competency experiment. So um, what, so that's the one where you have this array of numbers, like 1 through 10, they're scrambled up and you're trying to get them back 1 through 10 by doing swapping, okay? And it dawned on me that, well, there's actually two things in that box. There's numerals that are getting rearranged, and there's numbers, which are where the information is actually sitting and the constraint is actually sitting. And you're basically using the number information and comparing current positions to the number ordering. Numerals don't have an ordering property, they're just scratches on paper. And then as soon as you have that dichotomy, you now basically have the same dichotomy as the genotype, phenotype, blueprint, object that you're making, and so forth and so on. And so among those, and that confers then a number of interesting properties. First of all, you can swap things at the blueprint level and not necessarily get any change at the phenotype level. Or maybe you do, maybe you don't. And that's the sort of option that lets the stress selection and genetic assimilation work and so forth. The other is that as soon as you think of it in terms of like these two levels with blueprint and the output, the first thing you want is to have parts. And so by analogy with the DNA, which is actually, I think, probably a pretty good analogy in many ways, you've got different bases. And then on the other hand, you've got amino acids. And then, so what actually happens with that? Well, you've got a very rigid code that goes from the DNA to the amino acids and thence to the protein. But which proteins you decide to make and how those proteins assemble or get assembled by another protein, that's the part that is subject to optimization, I would guess. And so if I were going to look for a place to apply a free energy principle, that's where I would guess it would look. Now, maybe in evolutionary history, there's a similar principle for just deriving a code. But in any event, so then now if you're looking for some kind of electrical code that's the analog to that, then A, you would like some parts. Sorry, if you're want an electrical blueprint that is the macroscopic blueprint that's constraining the organism, even if you push its eyes around or something, then A, you would like some parts of some kind, like sub-electric fields. And B, you'd like some code for how that gets translated over into actually building the organism. And then the funny thing about the genetic code, so we know about the reading frame as basically restricting how to go from ATGC to an amino acid. But I remember in grad school, I asked, well, okay, where is that code sitting? And where it's sitting is in the tRNA synthetase. And so then the question is, okay, can you look for analogs of all this stuff with the electric fields?
Mm-hmm. Mm-hmm. Yeah, I mean, you're right. You're right in that it's really critical for all these bioelectric states to ask who the interpreter is. So the mapping, right, much like with the DNA, the mapping between a distribution of voltage states and then some anatomical, state later on is really critical. And we spent a lot of time, and we're still thinking about. Originally, we thought that it might be specific voltage levels mapped to specific organs, and then we saw that that wasn't right, and then it really appears to be a pattern, differences across space. So what was all the interesting thing happens when certain cells of a particular voltage are sitting next to cells of a different voltage, and it's the difference that's actually meaningful to the outcome, not the absolute values of either side. It's the difference that matters. And so all of this brings to mind, okay, well, who's reading this? What's the interpretation machinery? So we have a few models now. We put out one, and there's one that's in revision right now, of asking how does a collection of cells read a spatially distributed bioelectric pattern and turn on specific genes as a consequence of this. So not an individual cell voltage turns on genes within that cell. That's kind of easy, and we found that years ago. there are 5 or 6 different transduction pathways that do it, but much more interesting is how do they recognize a pattern, and how do they know if the pattern is correct? How do they know what it means, and so on? Mm-hmm. And so that's what we're wrestling with now, and there's definitely an interpretation issue there. And so there are, we have a computational model of how that happens. It also, I think, ties into a very deep issue about memory, because there are these memory transfer experiments, right? Where you transfer, somebody like David Glanzman might just transfer RNA from a trained animal into a naive brain. We've transferred pieces. So we'll do things like transfer pieces of an animal from one to another, and we look at propagation of morphological memory, propagation of behavioral memories, and so on. And you have the same issue with the decoding on the other end. So the thing that's always bothered me about, and it's not just for RNA, it's for any material substrate for memories, is that if I train an animal to some sort of weird relationship that never, sort of not evolutionarily prepared for. So, I don't know, 3 yellow light flashes means take 2 steps to your left, or otherwise you get shocked, right? So animals can learn this. So let's say that ends up being encoded in an engram of some kind of crazy molecular structure. Maybe it's an RNA, maybe it's something else. I take that, I shove it into a naive brain, and there's got to be a decoding mechanism that can look at that structure and go, oh, look at this hairpin turn. Oh, I see 3 yellow light flashes. Ah, right, got it. Well, where's that code book? And you can imagine something like that, something for something evolutionarily expected, like fear of the dark or something. We can all share the same code book because it's built in. But for these really arbitrary things that is not plausible that we share a code book that already pre-specifies that, it becomes really hard. And then the worst problem is, it's bad enough when you're moving it from body to body, but recall within the same body is the exact same issue. Because for me to read my engrams, I don't have access to the past. All I have is whatever was left, whatever traces were left in my brain and body, right? Maybe not even just the brain, but I have to interpret those. So 3 hours from now, I'm gonna have to interpret whatever was left by past me as a message to my future self. I have to do the exact same thing. I have to look at whatever this is and figure out what they mean, and just sort of on the fly keep rebuilding this. Yeah. So I think I don't know, Chris, what you think, but I think this interpretation machinery is really the key to all of this.
Yeah, I agree that it's a very interesting and very tangled issue. And if you think about an electric field, for example, and you want to think about components, then really the only options are charge center locations which you could mix and match into an electric field to change its shape. Or frequencies, mix and match into a field to change its temporal shape. But that doesn't give you a whole lot to play with. And in the developmental setting, it's not clear that frequencies are playing a role. Whereas in the brain, for example, they clearly are playing a role. So, which degrees of freedom in the encoding itself is an interesting and difficult question. What counts as a component? But in the developmental setting, it's very clear that you have cells as components. So you have components in the reader, even if you don't have components in the source. And so the question becomes, how do the different components of the reader communicate with each other about their joint interpretation of the field? So the field becomes one communication medium that these multiple components have to jointly interpret. But to do the joint interpretation, they have to somehow talk to each other. Otherwise, they would have no basis for knowing what a difference is, for example. Mm-hmm. So we're faced in this case, I think, with a minimum of two different languages. The language that's embedded in the field itself talk to each other about their local measurements. So they may be talking bioelectrically through gap junctions or something. But that's a code, a bioelectric code that's in addition to the overall code that they're reading.
Can you get?
And this is.
Oh, go ahead. Sorry.
No, I was going to say, and this translates into thinking about natural languages in terms of, positional effects and grammars and that kind of thing that influence what the semantics of the different words are.
Can you get any traction, or is there anything that gets provided by either having some of this bioelectricity being a carrier wave for something, helping individual cells contribute to some overall pattern that then gets communicated back to each of the guys who contributed to the party, or resonance doing something like that?
Yeah. We don't have any data yet on resonance, but I think you're absolutely right in that. Well, first of all, the carrier wave business. So every cell by itself during the cell cycle and just sitting there, it has these little fluctuations of VMEM, and so in addition to that, whatever bioelectrics they're doing as part of patterning has to sit on top of this baseline. In fact, back in 2000, when I was first talking about starting to try to manipulate resting potential, this is what everybody said, is that well, this is a housekeeping parameter. You can't mess with it, otherwise the cells will die and nothing will happen. So yeah, they do have this like baseline wave, and then on to everything else happens on top of that. So I think the carrier wave thing makes sense. Also, I think it is true that functionally the electrical activities of these cells are added up to what in effect is a global computation that then ends up, it's the same. I mean, it's funny, the interpreter is the same cells as the generator in this case, because the cells, right, they have to generate these patterns. It's the same cells that are then going to read that pattern and do something as a result. So they're sort of talking to themselves in a way. But there's also a jump in level of organization, because by what the computations that they're doing by this bioelectrical signaling take place in an entirely different space. So the individual cells are computing things like, when do I divide? How's my metabolic state? Who's my neighbor? This kind of stuff. But the collective has to make decisions about huge things like, how many fingers do we have, and where do the eyes go, and how many eyes do we have? Right? It's an entirely different problem space, and so that they're executing these computations as part of a collective intelligence, which then immediately filters back down and says, okay, you're going to be a bone cell, and you're going to be a nerve cell, and you're going to be a muscle cell. But that isn't what the initial computations were. It sort of comes up and then goes back down.
So since you mentioned the computations, another thing that this two-level hierarchy, the genotype-phenotype kind of hierarchy, or syntax-semantics kind of hierarchy, buys you is the ability to do particular computations instead of mixing. Do you guys know about William Abelers' particular principle?
I don't.
So I can send you guys the paper. It's actually, I think, very important, and almost nobody knows about it. But so the question is, if you have red and white and do something, do you get some variations of red or white, or do you get pink? And one of the reasons Darwin was stuck with going to Lamarck was not that he liked Lamarck, but he couldn't see any way out of the red plus white equals pink. Whereas as soon as you have a genotype and a phenotype, you can now be mixing the genes, and so in the case of Darwin, so you've got tall and short. Well, a couple generations down, everybody's going to be in the middle if all you do is mixing. There won't be any tall people or any short people. And so how do you get out of that? And the solution with genes were essentially they do the particulate computation. So you don't lose the identity of the original elements of the computation. They're still sitting there. You just recombine them in different ways, and then you now generate a phenotype from the new combination.
Mm-hmm. Yeah. Mm-hmm. Yeah. You had some other stuff.
Now, when we think about writers and readers being the same systems, it naturally leads one to think of the field as a memory structure. Mike, as we were discussing with Santosh the other day in computational meeting. So you can think of the cells as writing to this memory structure and then reading from this memory structure. But one memory can also read from it. And they may be reading from it in a different language than you wrote to it. So the collective may be interpreting the same memory structure using a different syntax and a different semantics from the entities that wrote into the memory structure. And in a sense, you see this in the genetic code because you have coding redundancy for amino acids and different codons code for amino acids with different efficiencies because of the kinetics of the different tRNAs are different. But from the protein's point of view, and hence for the evolutionary system that's selecting changes in the genotype, it may not be sensitive to that language at all. It's sensitive to the reproductive capacity of that entire system, be it a cell or an organism or whatever. So it's the collective is speaking, in a sense, a completely different language from the codon language that's spoken by the DNA, that's used by the DNA to write the instructions for proteins. The proteins in this case are serving, in a sense, as the shared memory device.
That's nice. And it happens to work. That reminds me of an old paper, which I can also send you, having to do, basically the question is, okay, we speak languages, but we can also understand the guy. How is it that speakers and listeners converged on using the same language? You know, human speakers. And basically, if you introduce a couple of constraints, which in my case, I think turns out to actually be an analog to a reading frame that I think languages use. But you introduce a couple of constraints, and then it's not all that hard to converge on a common generator, you know, reader and writer that even if they're different, can at least understand each other.
There's another lens on this too, which Josh Bongard and I just put out a paper on polycomputing, which is this idea that you know, the exact same set of physical events can be interpreted in different ways by different observers, and thus be doing different computations literally at the same time. And so we talked about he and his student Atusa have this amazing sort of mechanical example of multiple computations being done by the same, you know, piece of particulate matter. And I picked out a bunch of biological examples from that paper where basically one way to the title, which Josh came up with, is there's plenty of room right here, which you know goes back to like this idea of room at the bottom, right, Feynman's. And so this idea that in biology there isn't any room anywhere else because it's all packed full of stuff. There's stuff everywhere, and so the way to squeeze more out of it is to evolve additional observers who do interesting things with what is already going on, right? So as opposed to trying to tack on new mechanisms. And one thing that's interesting about that is that if what you're evolving is a new perspective on an existing set of events, it means that you don't risk breaking those events. That's completely different than trying to make tweaks and hope that you don't lose your past gains, right? You basically don't touch it's observation only, right? So you don't touch the thing that's going on. And as a simple example of that, we had this other paper recently where you take a gene regulatory network, and depending on how you look at it, meaning you pick 3 nodes and you call one of them the conditioned stimulus, one of them the unconditioned stimulus, and one of them is the response. If you pick the right nodes as your CS, US, and R, you can show that thing is doing associative learning, but only if that's your perspective on the system. If you have a different perspective, you'll see it doing something completely different. And in fact, multiple observers can have 2 different mappings, and they will see it. They will have 2 different pictures of what it's doing, but nobody's touching the actual network. You're not rewiring it. You're not changing synaptic weights for memory. You're not doing any of that stuff. It's literally what perspective you're taking as an observer. So, and there's many examples in biology. So that's another thing, right? You've got some kind of a encoding system, and it's working great for one thing. Pretty soon something will evolve which takes advantage of that just by interpreting that as a different kind of computation that you can make some sort of use out of, right? So that's kind of another aspect of this.
So basically what's going on is underlying it all has been some set of correlations, and then you're projecting it into some other world where it could have been completely gibberish, but at least they're still correlated.
Yeah.
Because they inherited the correlation.
Yeah.
That's cute.
That's cute. And I'll find it momentarily, but Jeremy Gay, who does all our graphic design, he did I asked him to do a version of the classic Gerd Lescher-Bach cover from Hofstadter's book. So he did an amazing version of that for embryos for us, which for that book, which I'll show momentarily. But that's exactly what you just said. It may, depending on how you look at it, it may look like gibberish or it may not.
Yeah, in a sense too, put this in more computer sciencey language, this is what interpreters and compilers are doing, but particularly interpreters. Right, you have down at the machine level, or slightly above the machine level, you've got a whole bunch of processing going on, and layering a high level language on top of it is layering an interpretation. It's assigning a different semantics to all of that processing that's already happening.
Mm-hmm.
And within that, using that semantics, one can interpret what's going on as, a Zoom call or something.
Yeah.
Whereas without that semantics, you have a completely different idea of what's happening.
Well, and look at how powerful that is, right? If you had a if you were running a software company or something, and you had a candidate that you were interviewing, and they say to you, well, I'm a reductionist. I don't, but I think there's no such thing as an algorithm. It's Maxwell's equations that govern what the electrons do. They just do what they're going to do. You'd never hire that person because they wouldn't be able to. They wouldn't code anything. It's hugely empowering to think that the algorithm makes the electrons dance, right? Because then you would go on and you would write things when you're thinking about it at that level. If you lack that abstraction, it's extremely hard to do anything. And I think here, check this out. This is the cover. So that Jeremy made, right? And so the idea is you've got the same batch of DNA. And so this in particular is our Xenobot example. You have the exact same batch of DNA. We don't change the genome, but depending on how that DNA ends up being interpreted, you end up with a frog embryo or you end up with a Xenobot. And it's the exact same, right? It's the exact same DNA that is somehow, what is it encoding, right? Well, it depends. It doesn't just encode a frog. Who knows what the heck else it, down here, who knows what else? So it's this idea of, I don't know, information or environment or something is sort of, is the prompt that gets this thing to generate. It's like a generative encoding of some sort, and there's a prompt that gets it to go in a particular direction, and you end up with something like this, or you end up with something like that.
Almost like a hologram, right? Because as I recall, if you shine the light in different directions, you get a different readout from your flat piece of hologram film.
Well, yeah, right, and that's interesting too. Back to the memory thing. So I think the point there is that you can store multiple images sort of on the same piece of film and just recover them with different signals. There's an amazing book called Shuffle Brain, and it's this guy Paul Peach back in the 80s who did all these experiments in memory in salamander, and he basically was, he started out by looking for memory and taking out different pieces of the brain and showing them, well, it's actually everywhere, and then he would move the pieces around, and the salamander was, would basically be completely fine and do all the tasks and everything, and then he would move pieces from goldfish to a salamander, and the vegetarian would become a meat eater, and the meat eater would become a vegetarian. It's just amazing. But the second half of his book, so the first half of this book is all these experiments. The second half of his book is a holographic model of memory, where he's sort of inspired by these experiments of non-locality, like he couldn't find it anywhere in any particular region and so on. He pulls out all these analogies of trying to store multiple different memories and whatever else is in there in literally the same hardware, right? They all have to overlap somehow.
Then I guess that gets us back again to what's the location where all this is stored? And your question of this macro storage thing, deducing the micro from the macro, roughly. And that reminded me, as I was reading this paper that you two wrote last year. And, one of the citations was to David Pines' paper from year 2000 about phenomena in physics that were macro, not deducible from micro. And I don't know enough physics to know where those constraints are stored. Do you know, Chris, how let's see, he gave a few specific examples. I took a quick look at it this morning. Um, uh, oh, um, the theory of everything paper. So he says the quantum Hall effect is one, Josephson effect is another, and you can't predict them from the micro level. So do you know where the constraint is coming from? I don't.
Well, in many cases, the constraint is coming from the environment, which is macroscopic.
Oh.
And is providing top-down boundary conditions of one kind or other on behavior that one can describe microscopically only by putting it into a kind of box that's specified at this larger scale.
Huh. Okay. So this is beginning to remind me of like gravity effects, your Markov blanket, and there's something else that just hit me on all this. But anyway, I see what you mean. Yeah.
But you know, this issue of where is it stored has been driving me nuts for a long time, because there are many such things. When you know, the distribution of primes and all the where did, like, that stuff doesn't seem to be you know, it doesn't seem to depend on the physical facts of the universe. Like, where is all that? Or even just the, you know, the thing where you've seen this Galton board. Yeah, it's just it's a piece of wood, and it's got a bunch of nails stuck into it. And you take a box of marbles and you dump it over, and they go boom, 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 and in the end you get this bell curve, right?
Yeah.
You always get the bell curve. So now you could ask, where is the shape of this bell curve stored? So you start looking at the wood, and you look at the nails, and then you look at the distribution of the nails. None of those have anything to do with, you know, none of them encode in the strict set. So where the heck does it come from, right? There's a million of these things.
Yeah. Why are there normal distributions?
Right, or truth tables, right? So you evolve. I like this too. You evolve a voltage gated ion channel, which is basically a voltage gated current conductance. It's basically a transistor. You have a couple of these things, you can make a gate. If you have a logic gate, you have a truth table. Where's this truth table? Like, you gain in the fact that, you know, the NAND is special and all this kind of stuff. Where is all that? It sure wasn't in your you know, ion channel design. It's you get that for free somehow. It's like this incredible free gift from I don't know where it comes from.
Huh.
Yeah, it's relational information that we typically don't know how to predict given the low level.
My quantum mechanics professor used to joke, we'd be complaining about how long it was taking to do the homework. And he said, yeah, but the atoms can do it like that.
Yeah. Well,
I could ask questions about the other topic, if that's okay.
go for it.
So this has more to do with the things and cognition. And I noticed a couple of things there. The Markov blanket way of looking at it took me the longest time to kind of wrap my head around that. And I suddenly realized that, basically, you guys in Tristan are trying to exclude stuff out in the environment that would normally just be bumping into the thing that you're trying to look at. Whereas I've been looking at it the other way, which is I got all these totally isolated parts. How do I put them together anyway to make something? But it's sort of the same problem. So like I've been looking at it from the construction point of view, and that's sort of looking at it from the installation point of view. And either way, you can make hierarchies out of them. So I like the idea of hierarchies of Markov blankets. That makes sense. And there's this old idea from I can't remember names anymore. G. Spencer Brown, Laws of Form, about drawing distinction.
Mm.
And near as I can tell, the Markov blanket idea is that, oh, that distinction actually has some structure to it. You know, like there's this, you can divide it into sensors and effectors and so forth. So that is all fine. And then, am I right that you guys are trying to find a general principle for agents that can do self-organization? And all I'm trying to do is find a particular organization used by humans. But so anything that I might say about language and cognition is essentially my proposal for the special case that probably satisfies the constraints that you guys have been working out mathematically. So I'm pretty much all fine with that, although I have a long list of things that I need to find definitions for before I can actually really understand, you know, all your derivations. But I've got the gist of it. And then in particular, and then Chris and I emailed a little bit, your reference states are, I think, exactly what I'm calling the specified relations that define the things. And your pointer states are the various substitutable ones that I've been saying that, well, okay, it could be this, or it could be that, you know, I could have a hat on or not, and it's still me. And so I think that is all in parallel. I do have one quick question. Is there an advantage to having pointers rather than talking about the state itself? Or is that just a mathematical convenience?
Oh, it's just a historically traditional name.
Oh, okay.
Physicists talked about pointer states, looking back to the idea of old analog meters that actually had pointers that could point to 1 or 2 or 2.5 or whatever.
Oh, I was
so
thinking
that's
more
where
like
that language comes from.
I see. I was thinking of like computer pointers, you know, pointing from here to there or something. Okay, I see what you mean.
Yeah.
Okay, all right.
No,
so,
it's a far older language.
Wait, I just got all tangled up. Okay, there's an advertisement for Bluetooth. Okay.
Right.
Yeah.
That's why the pointer states are the states that can vary.
Okay. All right.
Because the rest of the meter keeps its shape, and the pointer swings around from one number to another.
Okay. Then so far we're in agreement about what's going on. And then the only thing I would say is that the reference state is not something we identify, but the primitive cognitive act is to stipulate the reference state or whatever. And then that is what makes you now a cognitive organism, which I define as something that can detect things. Otherwise, it's just a bunch of flashes of light and noise coming and going, and I'm not cognizing. But as soon as I can define a thing, then I'm capable of doing cognition.
Yeah. If I encode a particular reference frame that lets me identify a table, then I'm in effect stipulating what counts for me as a table.
Yeah. Okay. Oh, I see. So, okay, that's what.
And anything that fits those criteria is a table by stipulation.
Yeah.
For me.
Okay. Okay.
Maybe totally different for you.
Fine. Fair. And then what I would say is that various things you do in cognition, like an abstraction, are just moving things from one column to the other. So I've got a list of properties. I'll say what I mean by a property in a minute, but and those properties are either specified or substitutable, you know, your reference or pointer. And the substitutables, I think, are the same as swappable, evidently. And then, so if, for example, I say I have an organism and I stipulate that it moves and it eats plants, then, okay, that defines a vegetarian. If instead I say it moves and eats meat, well, that wasn't swappable. So the meat the meat versus plants was not swappable, I changed it down to definition level. Up at the phenotypic level, I've got now carnivore. On the other hand, if I move the bit about exactly what it eats from being in a specified column over to the substitutable column, I've now generalized from vegetarians and carnivores, I've generalized to animal. And so that you could pretty much do this on a laptop, I suppose. Just shuffling stuff from one column to the other is either specified or substitutable, and you do various cognitive things like, abstraction, definition, and then there's a hierarchy of things, I would say. So if you start out with percepts, those can only be created and destroyed. And the next level up, I would say, is you can have a set of them. I call them constellations, but you can't change them. They can only be created or destroyed. So they're still not things. It's a set of things in some sort of arbitrary relationship. But as soon as I have something that has both specified and substitutable, now I have a thing. And it is no longer just only created and destroyed. It can change. And that's what lets us do thinking.
Yeah, that's super interesting, because it ties to some stuff that I've been thinking about with respect to in development and metamorphosis and regeneration and all that, which is this old idea, this old ship of Theseus idea, right? And so thinking about the fact that the important thing about the ship of Theseus, as they replace the planks and all that, and it stays the same ship, is that what allows all this to happen is the policies in the ones doing the replacing. So it's the policies of the people, cells, whoever it's going to be, that are replacing the components that makes this thing the same, because they need to execute their changes in a way that preserves some kind of invariant for them. So they're going to choose where to put the boards and everything in a way that preserves what they think of as the ship. That's the only way this is going to work. So again, we're back to this idea of observers, and starting off with the notion that if you want the thing to stay the same despite molecules come and go in the body, cells come and go, if you're a cognitive system, ideas come and go and mental states come and go, but you're going to stay the same. For you to stay the same, there has to be a replacement policy of some sort. And then that gives you the idea, that gives you the ability to do what you just said, which is better than staying the same, is actually a policy for changing you slowly into something else. So, if you're a caterpillar, you are maintained for a while, but eventually there's a new policy that actually maintains you and it turns you into a butterfly. And, are you the same? You've got some of the same memories and you've got some other stuff, but a lot of things have changed. But it's all, it's all about the policies that are not just keeping you the same, but actually slowly transitioning you to some future, sort of representation of what you're going to be. And in order, and you to do that, you have to place the molecules, the cells, the information in the right places to be consistent. Yeah.
To take this back to the previous conversation, this is precisely the kind of relational information or boundary condition information that we were talking about with respect to Pine's paper earlier. It's exactly the kind of macro scale structures that aren't predictable, but they end up being stipulated by something, some aspect of the environment. In this case, the aspect of the environment is the actual user of the representation that says, what gives this representation an identity condition for me is a particular utility. And as long as I alter the representation in a way that changes that utility only slowly, I can count it as the same thing. Otherwise, there'll be some dramatic failure. Right? It loses its identity for me because it no longer does the job I need it to do.
Yeah, an analogy I have for that is sort of like jokes, where there's this cartoon I saw once where somebody goes up to his bicycle, he grabs it, he starts to walk with it, but the rear wheel stays right where it was. Well, okay, so you can define everything like being next to each other. That does not yet get you a thing because it didn't have any utility anymore because the the wheel was still there. So there's a little more than just spatial location.
Yeah, they're lovely old experiments by Elizabeth Spelke and her various collaborators
Hmm.
with infants in the kind of 3 to 6 month old range, in which they, glue various parts of things together or detach them in ways that lead to uh, surprising conjunctions of things or disjunctions of things following manipulation. So, for example, they have a toy person and a toy car, and they manipulate them separately. And then they present the infant with the toy person glued in place in the toy car so that if you pick up the person, the car comes too. And at 3 months old, that doesn't surprise the infant at all. But at 6 months old, they're very surprised and react in a stereotypical way. So they've developed this concept that these are two different things, whereas before it was just all one connected sensory mess.
Yeah, that's nice. That's nice.
So you can actually see these capabilities developing in real time.
So I should say then a little more about what I think a property is, because that might sort of be relevant too. So the properties I think of as two entities and the relationship between them. So like if you're trying to define a snowflake, it's going to have, like a six-fold symmetry and blah, 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 and it'll be cold and it'll be white and so forth. But all those can be expressed as two objects in a relation or two entities in a relation, and each of those entities is in turn defined by two entities in a relation. And so you get this hierarchy. And then if you take the specified and substitutable thing, where that sits is in the relationship rather than in the entities. Now, the entities have their own specified and relation, but that's inside them. So then what happens, for example, is if you say, well, okay, I have something, I'm looking at two things out in the world. One of them has exactly the same parts, that same component entities, but the relationship to the world differs. You would say, oh, that's particle motion. But what happens if you have the same relations, but different entities? Oh, well, that's what a wave is. Because you got the same relationship, but it's made out of different particles of water. And then what happened with language is that one day I said, oh, well, does this work for language as well? And, are we thinking entity relation to entity in our language? And the answer is in English, yes, but you don't notice it right away because we leave out most of the system component relations. And so you have data compression. That makes doing Chomskyan linguistics, which I think is basically correct, very, very hard and complicated. And then other languages like Japanese are entity relation. But again, you have this like reading frame that has to be imposed externally. It's external because words are, most words have multiple meanings. We can still understand it. So it's imposed externally. So it's again a macroscopic constraint that's sitting on this and imposes this pattern.
Yeah, another form of stipulated relational information at the high level.
Yeah. I would say it's wired in your brain, but we can't talk any fMRI people into letting us do the experiment or NSF into letting test. You could test it with like these eye flash kinds of experiments, but you can't get NSF to pay for it. Actually, so that I wanted to ask you guys. So for a paper like you've been doing on the free energy stuff, I mean, it can't be easy to find reviewers for a paper like that, right? Never mind a publisher.
It seems to take a lot of the editors a long time to find them. That's for sure.
Okay.
Yeah, well, yes, it's hard. This is a generic problem now anyway. Finding reviewers for anything is really hard now.
You find that really?
Oh yeah. Oh, even relatively mainstream things that are not nearly as interdisciplinary as this, straight up biology papers that we put out. Oh, it's brutal. Yeah, finding people willing to review things is really tough. For sure. I've been editing a bunch of guest editing a bunch of issues and whatever. And so I see it from the other end. It's like, it's very hard.
Is that because people are so busy or because they don't want to deal with new ideas?
I think it's mostly because they're busy. We get, I mean, that's what happens, right? So a lot of people are busy, and eventually you end up with a kind of a self-selected group that either that wants to review it. Why do they want to review it? Either because they're really into it, or and if they're really into it, they may have an axe to grind, and so they may not like your view on it. They have their own view on it, right? Or there's some other reason why it's gotten way harder. It's gotten way harder. Okay. Publishers is easier. I like we've had a few things in places like Entropy, which it's nice because Biosystems, Entropy, like these Royal Society, they're good with really interdisciplinary stuff that would be hard for a conventional journal.
Yeah, Royal Society we finally tried, and they were quite nice, but they couldn't find any reviewers, which I was surprised. But you're saying I shouldn't be surprised.
You should not